Hello and welcome everyone to our virtual road trip session. I'm Molly Soltis with ATS, and I'd like to thank you for joining us today as we visit Dr. Geoff Rowe, who will share tools he's used to aid in asphalt forensics and share some pretty crazy pavement failures he's encountered over the years. Now, if you've been on one of our trips before or attended a Zoom webinar in general, you know where the attendee controls are. Just a reminder, you're all muted and you can type your questions in the Q&A box at any time. Following Geoff's presentation, if you'd like to join the conversation, you can raise your hand and we'll unmute you. So today's co-pilots are Geoff Rowe and Tanya Nash. Tanya Nash has been a part of the asphalt industry for 18 years. She earned her bachelor's and master's degrees from the University of Florida in biomedical engineering. Tanya is a professional engineer licensed in Alabama and Florida and is the pavement materials engineer here at ATS. Geoff Rowe is the president of Abitec and has been working with asphalt materials for 45 years and conducting forensic analysis of asphalt pavements since the 1980s. He serves on many groups advising research that impacts specifications in North America, Europe, Asia, and Africa. He is a licensed professional engineer in the United States and a chartered engineer in the UK. So now I assume your seatbelts are fastened and your luggage is stowed, and we'll get going on our trip. So I'm going to pass it over to Geoff.
Hello. First, I'd like to say thank you for ATS for inviting me to do this presentation on forensics. I'm going to talk about pavement distresses I've observed in different places around the world and show you some tools for how I go about looking at these. This isn't going to be a complete covering of all aspects, but just give you a flavor of some of the things I've looked at over the years. So, pavement forensics. I'm basing this on approximately 40 years of doing work looking at pavements. Many things can go wrong. By understanding what can go wrong can guide us with the development of quality programs and help us to build successful pavements. There's many aspects to consider, from materials, construction environment, loading, etc. And we have to understand the environment our pavement is in. Now, what I want to do is, they talk about a road trip, so I'm going to look at a plane trip and look at some sites and things around the world as we have experienced problems in different parts of the world. I'm going to take you to some locations, some exotic, some not so exotic, but just locations around the world. So first of all, we have to understand the steps in this process. When we look at a pavement and we come to a site, we think, well, what information can we get? So we have to maybe look at doing some sort of desktop review, photographs, look at old reports, maybe understand the existing conditions. And then we have to decide if we need to do any testing, develop plans if we want to consider non-destructive testing and destructive sampling, look at visual surveys, other surveys. Google Earth is very useful for getting a good view of the site. Literature survey. Go and consult the literature. Many ideas can be developed from a review of information. Obtain the project information, contract documents, specifications, correspondence, site records, etc., etc., and include geology, site condition, rock sources, etc. Test data analysis, spreadsheets, a lot of data to look at. Whether we need to consider in our detailed plan development, things like visual surveys, destructive cores. And then there's various sorts of testing we can look at: falling weight deflectometer, dynamic cone penetrometer, LWD, cutting slabs, here are GPR radar on a site in New Jersey we're looking at. This is here as a site in Turkey we were digging up. New Jersey, Texas, and another one I think in New Jersey. Now, there is some published information that helps us. NCHRP published a guide in 2013 about doing forensic investigations. Quite useful, mainly aimed at agencies in the US, but it gives us some very useful information, and there's some indications in there on the sorts of things you should consider. So if you're new to forensics, it's certainly worth looking at this document, which can be downloaded from NCHRP's website. Just search on the name. Other resources which is useful to look at, look at the MS-22 construction of hot mix asphalt pavements. That's a fairly new edition published by the Asphalt Institute. Good source of information. I quite like looking at this hot mix asphalt paving handbook. My old friend Jim Schrockman had a large degree of input into that, and this can actually be downloaded free of charge. I've given the link there for that. Even though it's now 20 odd years old, it's still very useful information. The other thing that you can download available online is a distress identification manual, and the most latest version I think is about 2000-ish for that as well. But there's many other resources in published literature we can look at. Remember, we should always be comparing our assumptions and findings to published work, and in terms of published work, the published work should be sufficiently established to have gained general acceptance. So that's normally the test that we're using when we're trying to do forensic work. We have to understand the whole process. This slide is a little bit busy, but we have to understand everything from quarrying, the rock sources that we're using, crushing, how the material's crushed, what stockpiling arrangements are there, how the stockpiles are constructed. Look at the asphalt, the bitumen supply, additives, how that goes into binder storage, and then we have to consider a HMA plant. In this case, this is a batch plant. This is in Africa, and this is of Chinese construction, but it doesn't make any difference. They're basically all the same similar styles of plants that we see. Have to understand the feed systems, and then after looking at the feed systems, storage systems, mixers, screens, understanding the whole process here, we start to then consider the trucking, laydown, compaction. And then if we also need to consider things like soils, foundation, climate, the water, where the water's coming from. Also go to the design, the spec book, test data, contract documents, traffic forecasts, etc. And if we get all of this information right, we'll get a road with good performance. If something lets us down in one of these processes, we will not have a good-looking road like this road here in New Mexico that is really performing nicely. So we have to understand the whole process. When we look at test data, we have to ask ourselves what this tells us. How is it sampled? Is it representative? Is it a true representation? I'll look a little bit at some of these aspects later on. But, you know, one of the things that I'm always big on is making sure we get a good sample. How's the sample platforms at the plants? How is the sample actually being taken? What's the arrangements for quartering and dividing the sample afterwards? So we have to make sure we have a good sample to see what we're looking at. Then I come to my Asphalt Man Tool Box. I have 3 favorite tools that I like to look at whenever I'm coming to a site. And these are basically listed here, and I'm going to talk about each of these. First of all, I like to ask myself, is the material segregated in any way? So if I'm looking at a distress on site, quite often we'll see some segregation behind this. And I like to look at plots of binder content versus the fine content. And we need to consider this when we're looking at distresses. Volumetric charts, I like to build on the concepts developed by McLeod, John Edwards, who was one of my mentors in my younger days, and others. And as an industry, I feel that we're hung up on the reliance of individual charts for each volumetric parameters where these can be combined. And then thirdly, use of calculations of the effective specific gravity of the aggregate from GMM and PB, or a PB estimation from GMM and GSE. And you know, why do we do this? Well, in production, we want to see GSE remaining constant. A little bit more about this in a minute. So first of all, we have to recognize that binder is mainly associated with fines content in an asphalt mixture. Variability and bias in test data can be associated with segregation with, say, bad sampling or bad laydown or some other reason. So how do we look at this? Very simple way. We take the percentage passing a sieve that divides the fine and coarse aggregate. In this case, I generally prefer to use a 2.36 millimeter number 8 sieve. Sometimes other sieves, depending what's available in the aggregate gradation. If you look at this plot here, this plot has been generated from surface area factors, and you can see percent binder versus percent passing 2.36. We get a slope here about 1.13, something like that, and I'll see this slope, depending on the mix type, varying between about 0.1 and 0.2. And if we have scatter about this line, so if I have results that are around about this line, then it would tend to suggest that we have segregation. If it's a buckshot and the numbers are all over the place, then it would say that we have poor plant control or some other issues affecting the results. So that's an important check to consider. So going on, volumetric charts or chart. So if you look at mixed designs, since we've been doing mixed designs since around about mid-1940s, we've been plotting individual parameters such as percent air voids, VMA, voids filled with asphalt against binder content, and this is taken from the latest edition of MS2 in 2014. So that experience is now, what, 80 years old? But more recently, only some 60 years ago, MacLeod advocated that we should use singular volumetric charts. And the current practice is to use individual graphs. And I say, why this? It drives me nuts. And I put this angry man here because I really think we have a better idea. And in the last 30 plus years, I've been using a singular volumetric chart, which is this one. This curve shows the same data that we had in those 3 previous charts, but just combined into a singular chart. And here you see the data. The data on the previous slide showed that we were a little bit deficient on VMA. This is the specification box. So just a word to explain what this chart is. So on the horizontal axis, we have volume of binder, not the mass of binder. We know mixtures work volumetrically, so why not use the volume? It's the effective volume of binder. On this vertical axis, we have VMA, and you'll see the numbers run from low numbers at the top to high numbers at the bottom. Volume of stone on the other vertical axis, and you'll see 92 corresponds to 8 and 78 corresponds to 22. And then we have sloping lines, diagonal lines, which represent the air voids, and raking lines that represent voids filled with binder. So you have all this information on one chart. A typical mixed design looks a bit like a Proctor curve, and the maximum aggregate packing occurs somewhere here, and you can see this is the 4% air voids line, which is what we use for Superpave mixed designs. Now, in terms of this design here, which is taken from that same data set on the previous page or previous slide, taken from MS2 in 2014 edition, the design is deficient in VMA. So we know we need to do something to open up the aggregate to make a curve, say, in this region here. And we know that as we move this material or this design in this way, with a VMA which is higher, the volume of binder will go up. And generally we know that with a good mixed design, we typically need about 10% minimum volume of binder. We don't want to have a design over here. We want the design in this region here. This is another example. This is from the SP2 Asphalt Institute publication, 2001 printing. And this is the IH43 design blend number 3 from that publication. And what I've also shown here is the compaction curve. You can see this design just meets gets into this specification box. In this case, the VMA had to be greater than 13 voids filled with asphalt, 65 to 75. Fairly tight design on the tolerance for VMA, but it depends on whether in the specification the tolerances are applied to the design point, or whether all the production, including the design, has to be within the tolerances set for the design. So that partly depends on that. Look at the angle of that compaction curve. See how that runs at a slightly raking angle and doesn't doesn't go straight vertically, but has a slightly raking angle to how that goes up. So that's the what deals with the volumetrics. The third item that I really always like to do and always like to consider is if you consider in the lab we measure GMM and we measure PB, but we normally consider those independent of each other. Somebody will report a binder content, somebody else reports a GMM, no one ever puts them together, but they can be combined. So if you remember the basic equations that we have for mix design, we look at GMM as being a function of the percentage of stone and the effective gravity of the stone, percentage of binder, effective gravity of the binder. We can do simple rearrangement and we can calculate GSE. So, or we can do a rearrangement for PB. I normally like to use the GSE one. But why we do this? Well, we want the GSE to remain consistent. If it doesn't remain consistent, what will happen is we'll get problems on sites with VMA, density, site air voids, etc., etc. So I like to see this consistent. Every now and then I see it being specified in some specifications. I've seen a plus or minus 1% in a specification. I generally like to use about plus or minus 0.02 in specifications or as a warning limit when I'm controlling jobs, even though I've sometimes used a slightly tighter limit, maybe plus or minus 0.15 as a tolerance there. So these are the three tools that I like to use typically when I'm looking at projects. Now, what I want to do next is have a look at some different projects around the world. I've got 10 of these examples that I'm going to include, and we'll just go quickly around the world and look at some different sites. So I put this one on as the starter. This is a project that I was involved in the UK. This is nearly 40 years ago now, back in 1982. I looked a bit younger and was a little bit more junior than I am now in the industry. We had a bad ravelling at joints and patches of ravelling occurred during construction when we laid a material on a bypass, a 65%, 37.5 nominal size material, HRA base course. HRA is hot rolled asphalt. And you can see we had stony patches and less stony patches. And the question was why is this occurring? And why are we getting this bad ravelling occurring? So we went and cut patches and took those back to the lab and tested those. And what we saw was this. We ended up with some segregated materials on site, and this graph is looking at the same sort of plot I would look at for segregation, but it's looking at percent coarse, so it's just the opposite way around versus the percent fines. But you'll see the slope is about the same, 0.12 here. And some possible reasons, we had to go and figure out why this was segregating. This has a gap grading. It's a very sensitive mix to segregation, gravel, some rounded particles. So we looked at the various aspects, and it came back to a bad skip design. And this is the plant that was being used, and there was, when you mix the material in the pug mill, it dropped into a skip, and this skip trundled up a conveyor, which you can see in the picture there. And as it got to the top there, it basically tipped over and dropped the material in. And the way it was falling into this hopper, you would get stones running down, and every now and then, not consistently, but every now and then on a truck, you would get a big stony patch of material, and this would result in those patches on the project, and resulted in that those ravelling issues. So they fitted some baffles and modified the design a little bit to correct that problem. We can see segregation in many jobs. This is a much smaller project. This is one in Florida. Here you can see segregation introduced by laydown. Passing number 10 here I had to use because there wasn't a 236 available. But segregation is an issue which can cause failure, and you'll see this on projects all over the place. But doing these plots, looking at the asphalt content versus the coarse fine split, can very easily tell you if you've got segregated materials. Now, I put this one on, and this is one of the favorite set of pictures that I've taken in my history. This is high in the Andes. This isn't actually a project that I was involved in working on, but it was constructed in a similar manner to one that we were going to build. So I took this picture in May 2016, and you could see here that end of truck segregation was very evident. And, you know, at the time that I took this first picture, I didn't fully understand why this had occurred. You know, this was just a drive along a roadway. I saw the road newly constructed, no lines on that road, and I thought, well, that's an interesting picture. So I came back a couple of years later and drove the same roadway again, and I looked at the roadway, and you can see this is the exact same picture, just 2 years and 2 months later. That location right there is this location right here. Bad cracking just after 2 years. And the question is why? So on these types of projects, a typical plant would be producing maybe 100 tons an hour, and the paving crew, they would get their truck of mix there. They could pave maybe 200, 250 tons an hour, something like that. So they'd get this truck paved, and then they would stop, have a cup of tea, and wait for the next truck. In the meantime, all of that material around the paving machine is getting cold. And there's your end of truck. It's a thermal segregation in effect. You get this material which is cold, and then they get the next truck and they pave that one and stop again, have another cup of tea, and so on. But you end up with this patchwork quilt as you're going on. So working with my client here in Chile, we basically organized the paving system that we would basically avoid this sort of stop-go construction that we had seen occurring on some other projects. So this was a learning from what we'd seen in other areas, and making sure this didn't happen on the project that we were looking at. And one of the critical things I would say is make sure that we get the paving crew together. We explain to them the whole process. So, you know, this is actually on that same site, high in the Andes, 16,500 feet paving, and basically trying to establish good practices for the asphalt plant, the operators and the paving crew, making sure they understand all the issues that we're trying to accomplish. When we're looking at pavers, we have to make sure everything is set correctly. You can see some cracks. You know, everyone very quickly wants to associate cracks with the mixed performance or something else, but sometimes we'll see cracks associated with pavers, screeds, etc. We have to make sure everything is done very carefully. This is, here I am in Africa looking at a Superpave mix as part of some of the early Superpave implementation. And this particular location, we had rutting occurring here in the near side wheel path. You can see flushing as well. A bit further on the road project, again rutting and flushing occurring. And then you got a little bit further on, now we've got cracking and slippage, and so it's a mix. What's going on? You know, one area is rutting, one area is cracking. So, we go back and we look at the volumetrics and the design, etc. All of these designs were a bit problematic. Remember in that other design I showed you, we had a nice curve over. Well, here we haven't got the curve overs. So this is suggesting something, awkward in the laboratory with these. We'd expect to see these things curving over. Went back and looked at, say, the GMMs and the GSE calculations from that. And you can see that this was the GSEs being used in the designs, and now they've got some numbers up here. Remember, I'm normally looking, say, plus or minus 0.2. So there's 8, there's 0.25. So this variability here is huge. Volumetrics are all over the place. You know, whether you've got material down here, which might be that's cracking if it was based on a recalculation, or mixed designs up here, the volumetrics are moving all over the place. And we had to ask ourselves why. I always like to look at quarries and like to try to understand everything that's going on. So here we have the setup of there's one of the hot mix plants. There were two locations actually on this project. This is the northern location. We had another southern location as well. This is the aggregate screening and processing area. And then just behind this, we had the quarrying area. And you can see there's a face here in the quarry, and there's another face over here in the quarry. And these were the two areas that were being mined to produce stone. The area over here is basically this area here, and they were getting a rock that looks like this. This area over here is this area over here, and they were getting a rock that looks like this. And these were the gravities of the two rocks. So I said, well, you know, okay, so how are you controlling, you know, how you're blending these materials together? Well, we're not. We might blast from here one day, blast from here another day. And, you know, what was happening is there was no control or no thought of the geology of the materials really going into the crushing pile. Hey, it all looked grey and dusty. That's fine. But, you know, what you end up with is the gravity of the stone going all over the place, and voids control on the mix, and VMA control basically being non-existent. Another thing, you listen to pavement engineers, and they'll say to you there's three things important in a pavement, and they'll say it's water, and it's water. I couldn't agree more. So you have to consider water and the way the water's behaving. So I thought I'd throw this one on just for fun. This was an interesting project. I'm in Kyrgyzstan, and went out to look at a road at a place called Al-Bashi. Really beautiful area. If anyone wants to be a tourist in these areas, this is a gorgeous place to visit. We had some cracks in the road pavement. You can see here's some centerline cracking. They decided to make some trial pits, and here you see that crack, and that keeps going on and on and on and on. This crack was deep. This crack is over 6 feet deep in the pavement system. And the question is why? What's going on here? So Al-Bashi is up at around about 12,000 feet, depending where you are. And they can have some very cold winters. So this is the road a couple of months before that picture was taken. And the real problem is differential freezing. You'll get water moving into the pavement base area, and it will cause this differential heaving. And the snow on the shoulders basically insulates, so you get more frost penetration in the middle, and the whole road is basically slowly bending upwards. Great book in the ASCE press by Doran Zubik gives a lot of information on some of that cold regions pavement engineering. Really a good read. If you can get a copy of that. So, you know, we looked at some of the issues on this project, such as where the water's moving and how it is. And really, it's you have to have superb attention to the detail of drainage design. We had a roadway like this that water was actually flowing all the way down this road through the subsoil materials and causing thermal or frost cracking in this region here. Even though the sides of the road were, you know, adequately drained, but as the water flows down, it comes to the sides and then freezes and causes a dam, and then the road cracks. Same situation here. All of this area here was basically damming up and causing a crack. The phreatic surface associated with these slopes, you'll be surprised at how, you know, if you don't have drainage blankets, you can get cracking in these pavement systems. This is another example. This is another project in Africa. We had poor performance after paving, so I went to the site here just to do a complete audit of everything going on the site. So a Superpave 19 millimeter mix. There was locations with cracking, patching, different types of performance. This isn't actually bleeding. This is where they've sealed some rough areas. They've gone along with emulsion and sealed it. So one of the things that we'd noticed here during their paving was that they quite often, well, nearly always, would empty their wings. They'd be like that other site waiting for trucks, empty their wings between the trucks. And this shows a location here where they emptied their wings. And I thought, well, I watched them do this. This was when I just got onto site. And then I walked behind the paving machine and waited until they'd paved this spot about here and took this photograph across, and we end up with this. Clearly you can see the segregated material in the pavement here as they empty their wings and pave on it. And most likely, this was one of the practices that had resulted in some of those other failures. We could see that in some cases we had segregation. So if we look at this data here from the 20th of February, we can see that that's, looking at the percent passing versus the bitumen, that appears to be associated with segregation. Some of these other days, maybe plant control issues, maybe paving practice resulted in some of those problems. Selection of modifiers, we've seen that being problematic and resulting in thermal cracking in some instances. So one of the things we always have to do is consider all the aspects: thermal cracking, fatigue cracking, durability, permanent deformation, water damage. Go back to your site, look at the climate, soil conditions, and pavement design. Be very careful about how everything is done. Modifiers aren't a solution for everything. They certainly help, some of the modifiers, if used correctly, can really help us out. But it's not it doesn't avoid the need to consider all these other aspects of material performance. Volumetrics, key to understanding of performance. And I'm going to show you this example. This is the compaction curve that I showed in that earlier slide. This is the same graphic from the Asphalt Institute data set. And you can see that, as the material compacts in a gyratory compactor, it will go along a line like this. So we are going to get scatter in our results. And typically, when we see a test result or test results on site and plot them on this type of chart, we should see the data being scattered about a typical compaction curve, something like this. And depending on whether you have air voids or VFA, it doesn't really make any difference. The scatter should always be the same sort of direction. Now, one of the things that we had on one project that I was looking at was this type of scatter. So remember on that previous slide I said they should be going in this direction. These are the quality control results going in this direction, and you see here in this direction. This was a base mix, and this was the implementation of the wearing coarse mix. I said, well, what's going on here? Why is this showing up in this manner versus the other manner? So there's some things going on, and it was the fact that the contractor in this case was adjusting the GMM to make sure his void contents were nicely in the specification. And if we look at this type of plot here, we can see, when I look at things as a trend chart rather than individual results, and I always plot things as a trend chart, here we can now see, day after day after day we had the exact same void content. But look how the GSE is flipping and floating around. GSE is calculated from GMM and PB, so obviously GMM and PB are floating around. But it just so happened that the void content wasn't. Doesn't make any sense. So we have to look at trend charts. If you see repeating constant values, it's a red flag. And in this case, we highlighted this to all the parties involved, including the owner, the contractor, the consultant. And we implemented correct quality control on site. And lo and behold, this is what we saw with the restarted production. We saw the quality control being produced in the right way. And, you know, one of the issues I said to both the contractor and the consultant that, yeah, you know, every now and then you're going to get a result that fails the specification. Doesn't necessarily mean that the material is bad. It might be that something's gone wrong with the laboratory technique or something else. So what this does is it creates a warning or something that you need to go and look at. But you have to start off with having the correct premise and the understanding of how this material behaves. And you can't do this if you don't look at the volumetrics in the true manner, and if you don't look at quality control trend charts for really assessing material performance. Finally, I'll come on and I'll mention this one. This is the roller cracking aspect. Really, you must always make sure that you avoid roller cracks when you construct pavements. A couple of pavements here. One of these is in Sri Lanka, one of these is in South America. But you know, when you construct the pavements, this was a paving trial we were doing, and we had to modify rolling patterns until we made sure that we could successfully pave without getting any cracking. This shows about the worst sort of roller cracking I've ever seen on a particular site. And you know, the answer was that, or the answer told to me by the contractor on this was, well, the pneumatic tire will get rid of these roller cracks. And I say, no, this is not what we see. These are defects that have been built into the pavement. Sure, you might smooth them out on the top, but those cracks are still in there. And over time, with diurnal and daily temperature movements, they'll tend to open up as surface cracks. So what I've shown you is some tools and examples of issues that I've seen in different places around the world. If you're looking at asphalt forensics or trying to understand problems on site, please keep an open mind and don't jump to early conclusions. Don't forget the basics. I haven't covered all issues. That would take way too long. I've just thrown on some issues that I think are important and some the way I approach these types of projects. Training on site for me is absolutely critical. Explain the operation, what the likely risks are, and the importance of the team. Build the team, make sure the team understand the quality control and understand what aspects that they can have to make the pavement perform better. Engineers, technicians, please read the guides and be aware of the issues that will affect quality. Please try to understand the full process. And I will leave you with that. And thanks very much. If there's comments or questions, I'm really happy to take them. Thank you very much.
All right. Thank you so much, Geoff. I think I can really talk for everybody. That was fantastic information. We really appreciate you joining us in order to present this. I do have a couple of questions in the Q&A. We do have a question. I know that you answered it in the actual Q&A, but just for everybody's information. The question from Steve McReynolds, we have one that says, have you ever relied solely on the air void value or permeability of the in-place asphalt to determine if it is segregated?
Yeah, that's a fairly straightforward answer. I mean, if you've got thermal segregation, you know, sure, you could do that. But to be honest, if you've got any sort of mixed segregation, you really got to look at what's going on in the gradation versus the binder content. And that's really my reliance. And that's my tool number one of my Asphalt Man Tool Box. And, you know, those three things for me have been a great learning experience, you know, with my mentors, you know, 30 plus years ago, and I've used them a lot. And that very first forensic I did back in 1982 just demonstrates how those fines are associated with the binder content. So
Very good. So I have a question from Abene. I am sorry if I mispronounced your name. It says, is there a standard or manual or document to know more about the single volumetric chart, the one that you show that's combined? It's a famous question.
The story of this chart is that there was a 1959 and 1960 paper by in the ASTM press, and that was done by. I'm just gonna have to go back to my note on this really quick now, but that was done by McLeod, and then the way I've used it, John Edwards and another gentleman by the name of Jim Coxidge published some information in Turkey in the late 1980s. I've put it into AAPT, into a discussion around about 2010, but there's not a single information. But I'm happy to share. I have an Excel spreadsheet that I use, and I'm in the process of writing a paper about that particular chart, and I'll make that available. Certainly, if through Tanya or Molly, we can make that spreadsheet available to anybody who wants it.
Oh, that'd be fantastic. I know that's a very valuable tool, and it's great to look at. Puts everything in one perspective, and it's hard to kind of correlate about 5 or 6 different graphs all at once.
Yeah, the other thing that I like to use it as an asphalt guy is when we're on site, a lot of the time we're talking to folks who are geotechnical engineers. So the engineer might know Proctor curves and stuff like that. It's the same science as the Proctor curve. Too much liquid, you end up with no space and flushing. If you're too dry, you're on. Most of our mix designs, we want to be just on the dry side of that optimum, and you can see that curve should curve over nicely, not like those other ones I showed in Africa that had the wrong shape. And it's great for spotting mistakes. So when you plot the data on that, every time I do a design check, I plot the data on that, and you can see the mistakes.
We have a question from Alexander Vivoni. He says, "Hi, Geoff. Alexander Vivoni from Brazil. How can we address the problem of determining the correct binder content when we use crumb rubber modified binders?"
Well, it's the same process. I mean, you have to again use a volumetric chart of the same way. The problem that we have with modifiers is whether we count those modifiers as part of the functional glue or whether we treat them as aggregate. So there has to be some sort of decision made there, whether they're functional glue or they're aggregate. If it's a coarse rubber, I would probably say it's probably behaving more as an aggregate. If some of these finely dispersed materials, it's probably more as a functional glue. But this is a question that has been discussed by Napa and various other folks as we are looking more and more at these complex modifiers as to, if you add plastic in a mix, is it behaving as a glue or is it just behaving as a little aggregate particle? I don't think we know yet. Napa, NCAT, these folks doing research work on this will help us answer that question. There is a plastics NCHRP research project about to start fairly soon. Hopefully that will fill in a few of the blanks and some of these other work ongoing. I hope that answers that question.
Kind of as an add-on to that question, it seems like a lot of the forensics that you do when you go out to the site and you're looking at different things, you come back, of course, to the mixture testing. But have you ever been to a site that you're investigating and actually have to go back to the binder source rather than the aggregate and mix source?
Yes, I mean we've done that. It's an aspect of we can't fail to neglect any part of it. I've seen some, very bad binder testing on site, and I have maybe in session 2 of this talk, I can show you a few tricks I use for looking at binder results on site. but you have to examine everything. I mean, that's why I put that whole process on there. You know, sometimes we're getting bitumen coming in drums, in barrels. Sometimes additives are being mixed on site, like we'll see the Masenza units for mixing SBS. We implemented those in Turkey, in Kazakhstan, in Afghanistan, and I saw my old friend Francis as part of the delegates here. We were using one of those on one of his sites in Kazakhstan. So there's lots of different things that can occur, and yeah, no, binder can be an issue, particularly if it's you know, we've seen that more of an issue with thermal cracking in some of the very cold sites that we've been on.
Okay. Let's see. I don't know if this is a quick answer or not, but what is the future deficiency in the pavement concerning check cracking?
The future deficiency is it has a tendency to open up over time. We had a project in Malawi that I worked on with John Edwards, and we had cracks which was so wide, and they all started off as roller check cracks. We really must avoid those. I'll break down with a PTR sometimes if necessary. The biggest problem is enthusiastic roller drivers getting on the mat and driving too fast. And you know, if you can get that mat compacted without getting those cracks initiated, you're going to have a much better performing pavement. And you can always do it if you have good roller techniques. Sometimes it's a bit of work to figure out how you do it. Maybe you have to adjust the mix as well, but you can do it.
Okay. We have a question from Alfredo Castro, and he's asking, is there a way to identify if the variation in volumetrics is coming exclusively from the rep variability? Especially over long runs, sometimes it looks like we get variations that come out of nowhere with the same plant settings and materials, yet we can come up with an air void or segregation issues.
Yeah, no, it's possible. I mean, RAP can be variable. Generally speaking, the information that I've seen has tended to suggest that RAP is not variable from the sources that I've worked with, but you can have variability being introduced there. Again, it's a question of trying to go back and look at all the processes. There's not an easy answer.
When it comes to RAP, it never seems to be an easy answer. We have a question that says, any tips to increase or open up the VMA when designing an SMA mix?
It's really a question of quality aggregates. You know, we all know that VMA is driven by the characteristics of the fine aggregate. You know, that's largely where the VMA is. Anyone who's been on a Bill Pine Bailey method course will have that drummed into them many times. And you know, it's really a question of quality aggregates to control that VMA. But again, you know, using that volumetric chart, we can very quickly see where we are, because you know, VMA is basically going to move that whole curve in one direction.
Okay. Let's see. Kalwa Matthias, they're asking, what is the recommended initial air void at field just after construction? And why don't we compact the HMA on site up to 4% air void to avoid further settlement?
Yeah, you know, this is a great question, and there's a big difference between what I would call some international practice and some of the practice going on in the US. We always had the feeling that when we were building projects in the 1980s and 1990s, that we would be designing these projects as certain air voids, and that's really where we're targeting on site. We would use tamping screeds to get that, and very heavy compaction, and we would be designing for much better air void condition in the field. You know, in the US, the practice has tended to be to accept a slightly higher air voids, then get secondary compaction with traffic. Now, you know, that's always a risk with that. You can get better compaction in the field if you use better plant and better equipment.
Now, wouldn't that kind of lean itself towards that Superpave 5 process where they're trying to design and compact?
Yeah, it sort of leans itself in that direction, yes.
Okay. Next question from Bob Horan. Have you used non-destructive testing equipment such as FWD to help with your forensic evaluations?
Yeah, all the time. I mean, the slide I showed earlier on had a picture there of FWD. I had a picture of ground penetrating radar. That was a project in New Jersey, but we'll use extensive FWD surveys, depending on where the site is. The other thing I will mention is that every now and then we'll be seeing Benkelman beam data, especially in less developed countries. So we'll see lots of different data, but we make a lot of use of non-destructive testing data, and we develop our own software for that. We have our own equipment, and we'll do that forensically on pavements. We've tested pavements after, say, some of the hurricane damage or some of the flooding, say, they had in Louisiana. Did all of that with FWD testing, tied it in with GPS and other types of analysis. So, yes, we do that.
Okay. We have a question from Surinda Samra, and they're asking, products, services, and systems implemented throughout the entire highway supply chain can be assessed by product approval schemes here in the UK, which work really well, extending the life of the assets. Is something similar operated, and would this help with some of the things that you've identified?
Yeah, what started off in the UK as a HAPA scheme, which is a Highways Agency product approval scheme, is a scheme that they went through where a product is evaluated for a period of time before it's granted use on site, and was particularly useful for controlling proprietary products. I would say in the US we have some certification of products in some ways, and for example, the Northeast has a scheme where they look at products where products have to be tested and looked at on site. So maybe it's not quite as formal as the HAPAS scheme or the UK. I think the name has changed now, and Surinda might correct the name, but it's a slightly different scheme now. But basically, that's worked very well, and I think those types of schemes are very useful, particularly for new products that are being implemented.
Okay. And we have one of the last questions that says, thanks for sharing your experience, Geoff. While dust to binder ratio is an important parameter in performance in mix design, some agencies do not consider it as critical in the QC process. How important do you think this parameter can be and its effect on performance?
Well, I would say that the dust to binder ratio is a parameter that was introduced to try to capture the effect of the fillers or the minus 200 part of the mix that we have. But the biggest problem with that ratio is it doesn't really capture the nature of that fines. So the first thing I would say with that is the dust to binder ratio is a poor qualification of the stiffening effect of the fines. There's some better tools that we have. The dust to binder ratio is critically important to make sure it's consistent. If you have a variable dust to fines ratio, you will have a variable amount of pasty, gluey material in the mix, and you can lead to deformation and flushing. I have we looked at a project in the UK on this, where there was different types of fines being used in I'm trying to think, it was a high friction mix, surface mix being placed in the southeast of England. There was a mix of gritstone, limestone, and hydrated lime. And depending on if you took the amount of the dust and divided it by the gravity of that material and then added that to the volume of the binder, you could track the performance nearly based on that amount of material. So it is a very important material. And, it's all of these things you should be looking at as a quality control. You should have an action limit on key aggregate gradations. Duster fines is one of them, passing 2.36 or your number 8 sieve. These different sieves in the quality control should have an action limit associated with them. So if something's changing, then you go and investigate and make corrective actions.
Good comments there. We do have a comment just saying that thank you, Dr. Rowe, for the wealth of information you provided today. Everything great information. I do have one last question for you. As you know, if we look at the failures and we have different types of things go on, and then we start going through your toolbox, we go right down the 1, 2, 3 tools, but everything looks good and you end up having great data, everything trends the way it's supposed to, but you're still getting failing either mix or the performance is not doing very well the way we feel like it should based on the data that's presented. Do you have any advice on what to do after that?
Call me.
I usually do.
It's difficult to say. I mean, there's every now and then you'll come across something that's a brain teaser, and you scratch your head and try and figure out why, and you'll try to get all the data, but pretty much I would say 99% of the time we can figure it out if we get the right information. Sometimes we don't get the right information. Sometimes I'll get asked to go and look at a problem with cracking. I'll ask them if they've ever had any roller cracking, and they'll turn their head and say no, and then I'll walk up and see a site like I saw on that last slide with that roller cracking. And you hope you're getting information, but sometimes you don't. We just have to try to understand the best possible way. But the beauty of these types of tools is that what we want to do is we want to try to learn from our experiences and build these into our quality system so we can make better pavements, better quality pavements. I mean, that's the goal at the end of the day.
Absolutely.
And most of those asphalt pavements are actually working pretty darn good. Most of them aren't failing. The example I'll give you, that problem that we had in Africa, where they were fiddling the data basically on the GMM. I said to both contractor, consultant, and owner, I said, this material's fine. There's nothing wrong with it. It's just they're misinterpreting the results because they're scared of something being outside the specification box. And really, we have to have a certain amount of common sense in the way we approach these things.
Absolutely. Well, all good information. I really appreciate you joining us for everything. And I'm going to hand it back to Molly to kind of close us out.
Yeah, absolutely. Thank you both so much. And Geoff, that was such a great presentation. And we can tell the popularity of it by all the questions that came in. So thank you all for submitting questions and helping us to carry on such a great discussion. This webinar will be available. The recording link will go out to you all via email tomorrow or Friday. We'll get with Geoff about that Excel spreadsheet. And in the presentation too, there's numerous great resources that Geoff has referenced. So thank you again both for your time. Geoff, thanks for joining us and letting us visit you on our road trip today. And we'll see you all next month for our next session. We're headed up to Bluegrass Country. Thanks, guys. Have a great afternoon.
Thanks everyone.
Geoff.